let's imagine that we take two parts of a walk. Our first part, displacement d1, let's imagine that we walk from some initial point. We walk 10 meters east, and that is our displacement d1. And then our second displacement, d2, starting from our initial final point, well, the initial final point, the final point after the initial part of our motion, the final point of d1, we then walk 5 meters north. So maybe something like this, and we'll call this d2. So what is the final displacement from our very initial point to our completely final point? Well, the final displacement will look something like this. The displacement vector will look something like this. There we go. So there's our final displacement, d, where we know that d1 plus d2 equals d. In this special case, because we've got east and north, I've drawn these, or I've made up these displacements so they're perpendicular to each other, so that we know this actually forms a right triangle. So in this case, we can actually figure out some characteristics of our final displacement. We know, because this is a right triangle, I'm going to write the magnitude of d1 vector as d1, which we know is 10 meters long, and the magnitude d2 is 5 meters long. We can figure out what the magnitude of d is. We know that d1 squared plus d2 squared is equal to d squared from the Pythagorean theorem. So what do we have? We've got that d squared is equal to d1, which is 10 meters, squared, plus d2 squared, which is 5 meters, squared, or 100 plus 25 is 125. 125 meters squared. Take the square root, and d is equal to, I've got it, 11.2 meters. 11.2 meters. Now, remember, last time we said when you take the square root, you could get a positive or negative answer. The square root of 125 could also be negative 11.2, but we have stated that our displacement, our vectors will always have a positive magnitude. So I'll take the positive number. The magnitude of d is 11.2 meters. All right, great. Well, that's a big step. How can we describe the direction? Well, we could describe the direction of d if we could figure out what this angle is right here. What's that angle theta? Well, in this case, we could use trigonometry. We know that the tangent of theta is equal to the opposite over adjacent side, which in this case is 5 meters over 10 meters, or 0.500 with 3 sig figs, so that theta is equal to the inverse tan of 0.500. On your calculator, this might be labeled as tan to the -1, or I tan for inverse tan, or INV inverse INV tan, or even ARC, arc tan, or maybe just A tan, for short for arc tan. Any of those are possible on your calculator. But if you take the inverse tangent of 0.500, we get 26.6 degrees. So theta is 26.6 degrees. Be careful. If you do this on your calculator and get 0.4636 something, your calculator is in radians mode. We will talk about radians at some point in this class, in this course, I should say, but at no point will we ever be using trigonometric functions, inverse trig functions, in terms of radians. Anytime we take an inverse trig function, it'll be in degrees. So make sure, you will want to make sure that your calculator is in degrees mode, and just leave it in degrees mode. If anytime you have to change it for some other course or something, always make sure you put it back into degrees mode for any calculations that we'll be doing here. All right, very, very good. So we have that d is 26.6 degrees up from this direction. Well, now I said for our walk east and north, But to be more general for us, we're not going to use these particular directions, but we're going to define a coordinate system, x and y. So in general, we will define our coordinate system so that x is positive to the right, the way I might have written east here, or the way I did write east here, and y is positive upward, what I actually said for north. And we can define our x and y any way we want, just like we did before. So let's make this a little bit more general, and we can apply this to any direction with a coordinate system. Rather than east, I'll be more general here, and I'll say in the x direction. And rather than north, I will say in the y direction. Okay, very good. So to describe our vector d, to completely describe d, we could then say that d is equal to 11.2 meters in, or I should say, at 26.6 degrees above the x-axis. All right, why are all those things important? Well, obviously the 11.2 meters, that gives us the magnitude of our vector. 26.6 degrees, that tells us the angle between our vector and a particular direction, the x-axis. But we also have to say above, because if we say 26.6 degrees from the x-axis, well, that could be above the x-axis, could be below the x-axis, could be out this way from the x-axis, could basically be on any kind of cone around the x-axis. So to be specific in this case, when we're talking about two dimensions, we need all those things in there to completely describe the direction, the vector d. 11.2 meters at 26.6 degrees, in this case, above the x-axis, above the x direction. Either one is fine. Okay, very, very good. So that's a way that we can add vectors and figure out what the quantitative sum of those are. Now I'm going to actually do I'm going to change this notation just a little bit. With this first vector and this second vector, this first part, this second part, there's a way of actually writing out this vector without putting all of this stuff in there. That's can be very, very useful. And that is the x direction. We can physically describe the x direction with a vector that points in the x direction. There is a very, very special vector that's called a unit vector. Now, what does unit mean? Unit means 1, like the unit circle, a circle with a radius of 1. A unit vector is a vector that has a length or a magnitude of 1. Not 1 meter or 1 centimeter or anything like that. This is actually a unitless quantity. A length of 1, and then it points in a particular direction. The unit vector that's associated with the x direction, we write as x, and then with a little different symbol on top. It's a little caret symbol, or what we'll actually call a unit vector symbol. So, and we'll refer to this as x hat. X hat. X hat is a unit vector. It's a vector with a length 1 that points in the x direction. So we can actually write d1 as 10 meters x hat. Well, now what does this mean? This is something that we haven't talked about before. What does it mean to multiply 10 meters, which would be a scalar, with a vector? What does it mean to multiply a scalar with a vector? Well, that's a very good question. Let's just take a look at that for a second over here. I'm going to erase this part. Well, what would 2 times a vector, say d? What would 2 times a vector look like? Well, we would expect that to be the same as, as d plus d. That makes sense. We would expect d plus d to equal 2d, kind of like we always do in mathematics. But what would it mean to add two vectors, d plus d? If we have some vector d, let's say this is d, and we add d again, well, how do we add vectors? Head to tail. So we put another d on there. There's d again. What's the sum? Well, the sum will go from the beginning to the end. This would be 2d. Well, so what does it mean to multiply a vector by a scalar? We end up with a new vector that's in the same direction as the old vector. So 2d is in the same direction as d plus d. But what's the magnitude of our new vector? It's twice as long as our first vector. Well, okay, so that gives us kind of a way of understanding what happens when we multiply a scalar with a vector. Whenever we multiply a vector, whatever the vector is, say vector v, with some scalar, call it a, we end up with a new vector in the same direction as v, same direction as the old vector, but with a magnitude that's equal to a times the old magnitude. So what this does is basically it just stretches v, or it could compress it, right, if a is less than 1. It just stretches it out, or compresses it one way or the other, so that the magnitude is now a times the old magnitude, but it's in the same direction as v. I'll just put in one exception to that, and that is, what happens if a is negative? Well, I'll hold off on that. We'll come back to that. What happens is, what do you get if you have a negative vector? Just hold on, we'll come back to that. Okay, so what do we have here? What does this mean then? Well, 10 meters times x would be a vector that's in the same direction as x, but with a magnitude that's 10 meters times the magnitude of x. But what is the magnitude of x hat? It's 1. As we said, it's 1. So the magnitude of this would just be 10 meters. But that is exactly how we just described d1. Wow, that's perfect, okay? So by just taking the magnitude of d1 and multiplying by x hat for a vector in the x direction, that is exactly how we describe d1. Well, how do you think we could describe d2? Well, pretty straightforward. It would be 5 meters times what? A unit vector in the y direction, which we would call y hat. You have probably seen unit vectors like this before, but x hat was usually written as I, and y hat was written as j, maybe with or without the hats on top. I and j, these are exactly the same things. When I talk about x hat and y hat, I'm just talking about these unit vectors I and j. Okay, exactly the same thing. But I will use the symbols x hat and y hat. And we can then write, very simply, d is equal to 10 meters x hat plus 5 meters y hat. Well, this is a very, very handy way of writing out a description for a vector. This describes our vector as completely as doing it like this. We could go from this way to this way, or this way to this way, either way. We can go from this way to this way, exactly like we just did here. We can go from this side to this side by just imagining, well, what if you knew d and theta, but not this term and this term? Well, you know this length would be d cos theta, magnitude d cos theta, and this one would be d sine theta. All right, very, very good, excellent. Let's take a look at a little vector algebra, some other ways of combining vectors. Actually, before we move ahead, let me just say a little bit more at this point. This format of writing a vector, of describing a vector, giving its this part in the x direction and part in the y direction. In other words, this part is telling us how much does the vector point in the x direction. How much is the vector d pointing in the x direction, in the x orientation. While this one is telling us how much is the vector pointing in the y direction. How much is the vector moving xy's, so to speak. How much is the vector pointing y's, so to speak, in the y direction. These are called the components of a vector. In particular, these numbers here are called the components. This vector, this number is called d sub x, while this one is called d sub y. And these numbers are called the components of the vector d. In other words, dx is called the x component of d, dy is called the y component of d. And likewise, if we had 3 dimensions, if this vector were actually pointing, say, somehow out here, we could also define a y-axis, and we would have a y component and a z component and a z hat. We would have another unit vector and another component, giving us 3 components for 3 dimensions. But for us, we'll stick with 2 just for the moment. So just let's keep in mind, writing the vector d without the vector sign, but then a subscript x, that's the x component, and then d sub y, that's the y component of the vector. Okay, great. Now let's move on and look at some more vector algebra.